Okay, so we start. Thank you all for coming. So this is the first BSCA Factory talk. We thought that it would be interesting as BSCA Factory to start some talks, to discuss, to be in a space for discussion, reflection, and create community for developers, for startups, for SMEs that are interested in AI and want to learn and want to discuss about AI. And have insights coming from experts. And today we have two experts coming from NVIDIA, and Christian Canton, the Associate Director of BSC, is going to moderate the session. And I think that with the expertise of these experts, we'll have lots of insights for all of you. You know that BSCA Factory is a new initiative that we have at BSC in order to promote the AI Factory development within the community of startups, SMEs, etc. We want Europe to become more autonomous in terms of AI and to have a real European value chain in AI and to have our own developments. We have to find a way to do it. It's not easy, but we have lots of technology, lots of expertise here and research. And I think that it's a big challenge for us, also for BSC, but we are very committed to that, and we start with this path. Okay, so I give the floor to Christian, and we start with the talk.
Thank you, Mariana. Thank you, everyone, for coming today. This is as you said, like the first session of many to come. AI Factory is going to be one of the big bets of Europe, and we're super proud that the BSC is going to be leading one of them. We're going to host them into the chapel where the previous Mare Nostrums were. In this path to create the AI factories, of course, we have the hardware, which is going to be very interesting to build, thanks to our friends from NVIDIA, which are going to provide the GPUs. But I think the very interesting part is going to be the software that we'll have to build on the top of that. There's going to be a lot of effort to be building all the pipelines, all the support, all the different layers that will be consumed by the AI factory, so that when startups and medium companies will come and try to train their models, they have it ready. And in this path to reach there, we think that it's very important that we have these sessions where we bring leaders in technology to talk about what they're doing. And it was this one is a very funny one, because it was like 3 months ago that I was attending CAPR with some folks in the room, and Jose and I and Nadine were having some beers, and we're like discussing on some technical ideas, and they were explaining what they're doing, and I was like, wow, this is super relevant to AI factories, and Jose was like, hey, I'm going to be in Barcelona, and Nadine also is like very keen to join me. So I say, why don't you come to BSC and give us a talk and explain a little bit of what you are doing at NVIDIA that definitely is relevant to AI factories. So that was the genesis of how they come here. And I'm looking forward for the future, like to keep inviting NVIDIA as a very trusted partner to keep sharing what they're learning in building like this amazing infrastructure. They have all the software stack that they have that we're going to be consuming. I will not take longer. But I wanted to introduce Nadine Chang, who is going to be providing the talk. She's a senior research scientist at NVIDIA in the Autonomous Vehicles Applied Research Group. She got her PhD at CMU with Marshall Hervé, of course, and Michael Tarr. And she focused on long-tail learning and visual language model applications. So if you received the NSF grant, congratulations. There's like not many people get that one. So like this is so good. And you are working now on multimodal language models for data curation and pruning, pursuit of hallucination, free and robust LLMs, and data-centric approaches to physical AI. So thank you, Nadine, for coming here. We also have Jose, who's very shy and didn't want to come to the stage and say and talk, because Nadine is going to be all the hard work. But Jose is a long friend from the house. He's been collaborating with BSC in the past. He's been like educated here in Barcelona, but you're like seen everywhere in the world. I know we met when you were in Australia, but you've been in New York, in California. Now you are at NVIDIA as a director of research and leading no less than the autonomous driving team, which is a super important big bet in NVIDIA. You are a luminary in many conferences, like we keep crossing paths for the last 20 years, and I see that you participated in all of them. And I also would like to keep working with you, and also like you keep helping us into this quest of the AI factories and beyond. So with no further ado, so I'll give you the baton to you. So
Yes, thank you.
no way.
All right. Thank you so much for the warm introduction. My name is Nadine, as he just mentioned. I want to make sure that everyone can hear me in the back. Yes, good. Excellent. Okay, so I'm just going to get straight into it. Today, I'm going to talk about less is more, accelerating AI with advanced data strategies. Before I start, I just want to get a sense of what's going on here. I want this talk to be more of a discussion-based, so a bit more casual. So first off, I'm going to ask, how many here work with data intimately? Got dirty with it. You work with it. You create data sets. Okay, I see a few. I see you. Oh, okay, more hands. Good. Okay. How many of you work specifically with models? Developing models, training models? Okay, overlaps. Excellent. Okay, I'm glad to hear that. So today I'll be talking specifically on data. I know modeling sounds a little bit more interesting, but bear with me. And so, okay, I already said this, data is boring. So instead, I want to start with numbers. Let's talk about that. As some of you may or may not know, Meta just spent $15 billion for a 49% stake in a data labeling startup, Scale AI. So what does this tell us? Clearly, they have a ton of data that they want to process and label. Right. So, and the fact that there's an explosive amount of data is not unique to a specific domain. We can start from something as generic as internet data that has become public in the 1990s. And we can see something like explosive growth in data in recent domains like autonomous driving, specifically in more recent years and for the future to come. And something as generic and totally different like protein structure, right? Where the advent of AlphaFold has increased the protein structure bank by 5x since its discovery. Now, I'm not an expert in biology or protein, so if I say something completely wrong, raise your hand and interrupt me. Feel free. So obviously, we have a lot of data, and this is not a new problem. So we have various ways to address this already. The first is an obvious one, label, right? Meta just spent $15 billion, and many more are going to spend even more to come, and they have already previously. But this is expensive, it takes a lot of time, and it requires a lot of storage to actually store all of these data points and all of these labels. Another way to address handling a lot of data and actually training with it is unsupervised learning, where you train without labels. But consequently, this means you need to train with more data. And this means, again, more cost, whether it's compute cost or money, etc. And in both of these situations, something that remains a challenge is the quality of the data. And usually what that means in terms of quality is, let's say, image resolution. It can't be too blurry, for instance. Or the annotation quality when you ask annotators to label for you, right? And when we talk about annotations and quality, something that comes to mind immediately is biases. So how many of you have been working with biases in general or have encountered biases in your data set? I only see one hand, two, okay. Okay, so this is a common problem, right? We all know that this is quite problematic and we need to fix this. But briefly, bear with me, biases tend to come from our prior knowledge in the world, right? So if I gave you a task, let's say, I want you to give me names of animals. You're probably gonna give me some common names, dog, cat, but you're probably not gonna mention something like manatee, because that's not something we see in our day-to-day lives. So what does this mean? It means that when we collect a data and label a data, we collect what we know is true and believe is important, which automatically leads to a data set that's filled with common objects and not rare ones, and therefore not representative of our world. Now, I'm going to try to also move this a little bit to healthcare, because I know some of you here work in healthcare. And it turns out, from my minimum amount of research, that biases exist also in real data in healthcare, where actually there was an instance where in the United States there was an AI model deployed, and it showed bias towards one race over the other because it was trained on the wrong data. So the type of data you train with is very important for mitigating this bias. And similarly, we see this bias also in synthetic data for healthcare, where because synthetic data depends on the quality of the original data, which we already know has biases, and actually the generation model, which we all know is not perfect. That means that synthetic data very easily also reflect these biases as well. Okay, so we have all these problems. Now, the goal of this talk today is to somehow give us a roadmap to achieve a manageable, non-biased data set. Now, that's quite a lofty goal. But for us, we have identified 3 key ingredients. To create such a data set, we must first determine what sort of data we want to add, how much data, and how do we actually incorporate all of this into one single data set. In this talk today, I'll be focusing more on what data to add in the form of data selection, where from an existing data set, we want to reduce that as much as possible so that we have a compact data set. And also in data curation, where let's say we have an existing data set and it's actually not sufficiently covering what we need to know to actually expand that. And also in error curation. I won't be touching as much on scaling laws and data mixture, as we leave that for a lot of important work that we have currently ongoing. So before we actually get into generic sort of data set strategies for all of these domains, I want to first look at each individual one. So for protein structure and generation, we see that the way that they handle the data pipeline is they generate the data, they put it into some pool, they make sure it's diverse enough and of good enough quality, and then they create a data set and they go off and train a model that can do drug discovery, et cetera, et cetera. And when we go towards a totally different domain, such as autonomous vehicles, this is a map in 2023 of all the deployed cars. We see that, again, I'll reference this figure. There's an explosive growth in data, but specifically, there's going to be even more in the future. And this is something that these companies are very concerned about because cars are already deployed, right? So this is a slide from Tesla. And I won't go into detail here, but what's really important, for example, for all autonomous vehicles companies today is that of the deployed cars, we need to make sure that any failures they encounter on the road, we can fix them. And currently they're doing this in a data strategy way. They take these failures and they incorporate the feedback and somehow include it into the training data set again and redeploy these models. And this is even more important in terms of selecting high quality data in foundation models. So I want to briefly define what a foundation model is, which is a massive model trained on diverse data sets for a variety of tasks, whether that's ChatGPT or Llama, or even like Cosmos for robotics from NVIDIA. And if we look at how they're trained, we see that it's actually quite similar to what we've seen previously. But here they collect data from the web or generate if necessary. And again, we go through the same process of data pool, diversification, and creating a data set and model. So when we see the development of foundation models, something that's mentioned over and over again is that the quality of data is extremely important. And we see this everywhere. Everywhere that anyone talks about anything on foundation models, they keep mentioning the word high quality data set. And so we're really in an era where data is king. But thanks to this foundation models, we now have amazing models with open world knowledge, which in this talk today, we'll be leveraging fully in order to create our generic data flywheel. So I mentioned a generic data flywheel. How do we actually get there? This was the original pipeline for developing foundation models I mentioned earlier. And you'll notice if I put it side by side with the pipeline for the protein, it looks very similar. And why not just use the same one, essentially? If we don't need to generate, then we can simply skip that step. And if we bring back the flywheel for autonomous driving and trying to address errors, we notice that there are only a few components missing that could bridge the gap between the two. If we move these components all together, what we see here is a full automatic pipeline and flywheel that can work with a variety of domains that are incredibly different from another. So in this talk today, I'll be focusing on how we actually get to this flywheel and each component of this. And I'll try to instantiate specifically for AV for now, but note that this is not restricted to that. And for now, I'd like to start with dataset and model. But before I get there, are there any questions? Okay, no. Okay, so earlier I mentioned that there's biases in labeling, etc. So when we talk about dataset and model, the first thing we think about is a common way to create a dataset is just to handcraft it, right? Something very commonly seen is ImageNet. There's predefined 1,000 classes. We go about and we populate these categories. Okay, great. But again, when we do creation of datasets, there's a lot of biases, right? So they require data labels, and especially for object detection, where the goal is to classify a variety of objects in one image, you'll see something that pops up is that when you try to increase the frequency of one object, you actually also increase the frequency of another object in the same image. And so this leads to a long tail problem that we see very frequently. And this is also true, especially for more complicated tasks like self-driving, right? Where the goal here is to intake all of the various visual information and sensor information and output a final trajectory for the car to drive. And so handcrafting a data set for such a complicated task, while there are some ways to do this, such as the functional scenario tree, is actually still fairly ad hoc because this is a fairly new domain and there's no sort of principled way to actually define the various actions that a car will take. Okay, so is there an alternative way to doing this? For us, NVIDIA, something that we've been thinking about and that we think is very important is to do this in a completely data-driven fashion. And I'm going to take a little bit more time here to talk about data-driven fashion and data space. And this is the main focus that I want everyone to take away from this talk. So when I talk about data-driven, the first thing I want to say is I want to take each data point and I want to project it onto a 2D space, right? So I made a blank square here. Of course, trying to understand the boundaries of all the data in the world is impossible. It's very difficult. But for simplification, we'll simply draw these 4 lines as our simple boundary. So we can create a data set from scratch with nothing, but as it happens, we tend to have existing data sets, right? We have that in healthcare, we have that in AV, and we have that in the internet. And so this is actually a really good way to instantiate the data space. We take our existing data set, we map it onto a 2D plane. Now, because data sets are biased, it turns out that we actually miss a lot of points in this space, right? And that means we essentially fail on those data points when we actually test these models. So our goal here is that we want to select and add data under the guidance of the current data set we have so that we can expand the total data space coverage, right? And if we have a mathematical way to define this data space and this data space coverage, we can actually do this in a very automatic process. So this is where some math comes in. I'm not going to go into too heavy in the math details, but Jose and I are happy to take questions offline. So I mentioned the data space. Let's put some definitions here. The definition of data space for us is a space in which all data related to the targeting task lies. And we can approximate this data space with an embedding space where we convert each data point through some encoder that can be then turned into an embedding. And key ingredients to this data space are 3 things that I really want to highlight. First is define the task. And I'm going to say this over and over again for the rest of this talk, because what's really key to the data space is being task specific. And why is that? Well, in this particular photo, the baby is learning how to crawl. But what's important for learning how to crawl isn't whether it's wearing a pink shirt or gray pants, right? It's more about the motors of the arms, etc. And the second is we need to choose the appropriate embedding space that can actually represent each data point in the eyes of the task, right? And lastly, we must choose the data that can be best used to approximate the data space. So without access to all the data for a specific task, we must decide what data to use. So I say this because if we had access to all the data for a specific task, I don't think we would be standing in this room here today, right? And so the best case for us is to use the data set that we believe that we currently have is best representative of that task set. So that could be your train, your val, or your test. And this selection depends on the task itself. And some other important things to talk about are measurements for this data space. I'll be talking about data similarity. And when I talk about data similarity in the embedding space, this means data that are close together in the embedding space are similar. Those are far apart are dissimilar. And for diversity, those points that are close together are less diverse, and points that are further apart are more diverse. Okay, so that's some definitions. So the first goal of today is to create a high quality data set from an existing data pool. And this we call data selection. So a data pool is collected under manual guidance with bias, right? So our goal with data selection is to try to automatically make sure that each data point from that data set, or a subset of it, I should say, is valuable and contributes to the task. And therefore, it's efficient in terms of data. We're not unnecessarily using more data than we actually need. And also, hopefully, along the way, we can choose data points such that there's no redundancies and also remove some biases. Okay. So how do we go about creating a high quality data set? The goal is to select a small subset of data that best approximate the original data pool. And if we actually look at this goal, there are already existing methods to address this. And something that's very popular is coarse set. But coarse set has a number of challenges. So for coarse set, they try to use the model itself to actually understand the losses, etc. And so it's very model based. And because they try to capture representative data, coarse set methodologies fail to capture out of distribution data, so OOD data. And this means that being model based and trying to find representative data points means that coarse set methodologies do not scale very well when it comes to large scale data or any productionization, especially, let's say, Christian mentioned earlier about AI factories, right? So instead, let's try to twist our goal a little bit. So here, what we propose instead is that we want to find a small subset of data that covers the same amount of area as the original data pool in the data space. And by doing so, we can capture OOD data and maintain representation. And furthermore, by doing this in the data space, the embedding is task relevant and therefore model agnostic. That means we can use any model that works on the same task. So I've been talking a lot about space coverage, but what exactly is space coverage? Here is a very intuitive way of understanding it. Space coverage, as we define it, is the coverage our data covers in the data space by a single data set. And our argument here is that the larger your space coverage, the more diverse your data is, and therefore the more data that is also captured and representative of your task, therefore leading to the best model performance. Now, it turns out that trying to actually measure coverage, space coverage, is a very difficult problem. So instead, something that we can do is we can say the space coverage between two data sets is actually the difference that one data set can cover for the other. Specifically, what I mean by that is if two data sets cover the same amount of space, then the distance between the 2 points, the distance between the points between these two data sets will be 0. And therefore, you can exchange one data set for the other. There will be a couple of math equations on this slide, but I won't go into detail again here. But as it turns out, that trying to mathematically solve the minimum coverage difference with minimum amount of data is impossible. It's an NP-hard problem. Instead, what we could do is we can take a step back and look at trying to solve this from two data points point of perspective. That is, if two data points are similar in the embedding space, then removing one will maintain the same space coverage even with the two. And by doing so, we can simplify this problem into a very well-known problem called deduplication. Okay, so I talked about similar data points, but what does similar actually mean? So we have this image on the top, and we have two options on the bottom, A and B. So the question here I have for you is which image is more similar? If you think it's A, raise your hand. Okay. If you think it's B, raise your hand. Okay, yeah. Of course, A looks more similar, right? There are actually two images taken from the exact same video about 5 seconds apart. But if I were to ask you why you picked A, would you say it's because they look visually similar? But if our goal here is that we want to make sure that we can not hit this pedestrian on the top that's crossing the road, would you still pick A as the most important image that's similar? If you still pick A, raise your hand. Okay, excellent. I think all of you probably we should hire you at NVIDIA. Oh no. Oh, now we're back. Yeah, so for B, something that's more content similar is having the pedestrian in front, right? So A is visually more similar, and B is content-wise more similar. So when we talk about deduplication and removing similar data points, again, this reflects why the task is so important. If your task is, let's say, scene recognition, then yeah, go ahead and remove A. But if your task is more similar, then if your task is about trying not to hit a car, then B is more important for you. And actually, it turns out there are data points that can be both visually and content similar, and that would be this image C. And if you were to ask me now which one I would remove, I would just remove C because it adds no value in either axis. Okay, so that was an intuitive way of understanding similar data points. But now I want to go back to the data space and actually how we can do this. So I mentioned 3 key ingredients: task, embedding, and data space proxy. And I have briefly touched upon 2 tasks. One is 3D detection for AV, and the other is AV driving. But notice that 3D detection can be used for any domains, right? It doesn't have to be AV, it could be classes or tumors, etc. And now we must answer the question which domain we must use, which embedding we must use for these tasks, and what is the data space proxy. And so, as I mentioned before, detection is very well known, and it's across many domains, so it's a very established task. This means that the trained data set is actually quite good already and quite representative of the task. And so for now, we're just going to say we're going to use a train set as our data space proxy. So if we first focus on detection, the first thing we have to do now is select the embedding. So we just talked about visual and content similarity. Visual is you can just pass your image into a vision encoder and get the embedding. This is a very well-known technique. Now the question is, how do we actually get the content embedding? So for us, we have been working on trying to create a content embedding, which we call holistic embedding. And this holistic embedding leverages an off-the-shelf multimodal language model. This means that we do not train it. We just use it as it is. And for the holistic embedding, what's key for us is that this embedding must capture low-level information and high-level information. So it could be something like very specific or just really high level about the scene in general. And so what we do is we have an input X, it could be an image, a video, etc. And we have a prompt and also a multimodal language model, right? And we can leverage prompts to get various types of embeddings from the multimodal language models. And importantly, because we use any off-the-shelf MLLMs, we're agnostic to which MLLM you select. So if you want to use something from Meta, you can use it. If you want to use something from NVIDIA, which that would be great, you can also use that. Or if you want to use your own, feel free. And because of the use of multimodal language models, we also have natural language, which allows our embedding to be naturally interpretable through captions. Okay, so if you're all probably familiar with how something like multimodal language models can have hallucinations, right? And so what's key here is that you can use any additional data that you have to actually mitigate these hallucinations. And for us in AV, what we have in addition to a video is the ego trajectory, right? And we can draw this onto the video, and this helps us mitigate hallucinations, aka like wrong captions, from the multimodal language models. If you're using YouTube videos, you can use a YouTube title or any YouTube metadata to actually guide your MLM to make sure you mitigate those. And so this is the ego motion that I mentioned earlier that I drew on. Okay, so now that we have the embedding, the question is the algorithm, right? How do we actually go about selecting it? So we do this in a divide and conquer manner. First, we take our existing data set and we convert them all into embeddings, into content embeddings. Then we divide this entire data set into chunks and groups. And within each group, we apply visual deduplication. Because we have clustered this data based on content, we have ensured that within each cluster, they're all content similar. And now we can remove anything that's visually similar within that. And now what we have done is essentially maintained content diversity first, and then visual diversity second. Okay, so I just quickly stepped through the embedding and a particular use case, which is detection for AV. And we have determined that we must use holistic plus visual embedding. And here are some experiments that we have done. And what we can do now is by applying the algorithm, on the left-hand side, you see that we can reduce the data set used to train a model, which is a very curated data set, by the way, by 30% and still maintain the same MAP. So this is significant cost, right? Imagine, let's say you train an MLM, it takes $1 million for one training cycle. 30% is $300,000. That's a big amount of cost. And furthermore, we see that we can actually reduce the total amount of data, even for rare categories, and still see improvement in the performance. So it's really not about the quantity, but the quality of data that you use to train your model. And so this is the most important takeaway message from this particular section, is that quality really matters more than data quantity is what we observed. And we can select the high quality data automatically. So this work is also covered in one of our papers, which means you can access the code and also the various details on the algorithm in your free time. Okay, so I'm going to move forward now to actually the next section, which is about data curation. But before I do that, are there any questions?
clustering, for instance, to take, especially for outliers.
Yes.
I would expect their embeddings to kind of have the same issues that you have with the model later. So how do you go about ensuring that you're not throwing out outliers by not considering their characteristics when you're doing this?
Yeah, that's also a really excellent question. I think one way that we observed is by looking at the size of the cluster. And something I'll talk a little bit further after in a later section is error curation, where we touch exactly on outliers of those clusters. And what we do now is we want to expand the data to include those outliers so that you actually consider the OOD data. So I guess to answer your question, specifically for clustering, you just have to look at the size of your clusters and you have to look at your outliers, right? But that's also why when we want to add data into the cluster, we try to add data that is furthest away from the centroid of the cluster and on the edges. And this is how you can make sure that you include the outside data points that are more on the outliers of the data clusters. Because with k-means, you're ensuring that every data point is indeed in one of the clusters. Okay, thank you. I think we do have to move on. Yeah. Okay, but thank you for the questions. Okay, so now we're going to talk about dataset curation, where we're actually going to grow the dataset, right? So in this particular case, what our focus here is diversification as we grow. So not just randomly growing the data with anything. So if with an existing trained dataset, we can select more data points from another pool to essentially maximize the space coverage, right? And I'm going to go through this a little bit more quickly in the interest of time and for more questions. And by maximizing the coverage, we can define this by maximizing the coverage difference by adding data, right? And so if you have two data points here, something very simple is that we simply take the one that are outliers, then that gives us the largest space coverage, and we add that into the data set. And by doing largest space coverage, we're ensuring that we're getting more diverse data set. And so there's, again, a lot of math. I'll go through this again a little bit quickly. We see that maximizing space coverage difference by adding data is, again, a problem that we can actually reduce to just add the most different data that maximizes the coverage. And so if we look at what this means, is that we can take the data points that is furthest away from the clusters and add that into each of the clusters. And you can see that in this diagram here. And when we actually look at the results of this dataset curation, we see that we can add, remember earlier we removed 30% of the data and we got the same performance, right? Now let's say, okay, we still have the compute to actually process the original 100% capacity. So we can add back in 30% more. And what we see is that we can actually improve the performance again. So this really talks about, when we reduce data, it's about removing data that is of low quality and therefore redundant. And if you instead substitute that with something high quality also, you can increase your model performance even further. And we see this especially true even in rare categories, right? You see that we were able to boost the performance of this rare category, which for us is bike growth rider, even further to the top. And this performance is actually way better than the original. And the number of examples for this category is actually way less than the original data set. And this is quite compelling result for us. Okay, so I kind of just sped run through the dataset curation, but happy to take any more questions offline about this. So now I would like to cover also error curation, right? So previously we were talking about generic data curation, but now maybe we care more about models that we have deployed and that have failed. So how do we actually improve these models over time because it's not like we train one model and forget about it. We keep improving and improving. So now I would like to move to a different task. And this particular task will be AV trajectory planning. And for that, we'll use a model called end-to-end planning. The reason we choose this task is because this is a model that's actually deployed and always a model that we're constantly trying to improve. And again, let's start off with holistic plus visual embedding and the train for our embedding and data space proxy appropriately. And let's just see what happens in terms of experiments, right? And so when we look at error data and failures for autonomous driving, for us, this would be a failure. The trajectory that's drawn on here is a predicted trajectory, and there's a pedestrian crossing the street. Obviously, if we did this, we'll kill someone, which is terrible, and we get into a lot of trouble. So to correct erroneous behavior, we need good behaviors in similar settings. Essentially, we need a data point that looks like this, but instead of hitting the pedestrian, we stop. And so this is a similar data point that we want to essentially add to our data set based on this particular feedback and this particular error. So again, we can define this and ground this mathematically. If a model fails on any validation data point, we basically assume there is not sufficient coverage of that data space in the train set. And therefore, for us to solve this problem, we now use the error data as a guiding point for further data selection to the train set. And when we actually do this, what we do is we take the videos, the error videos, we take the descriptions, we take the holistic embeddings, and we pick the ones that are closest. We pick the data points in a different data pool that we have never seen before that is closest to these failures. And we greedily add it into our data set. And what we see here is that even by such a simple methodology, we're able to reduce the total number of errors by 22% with only 1.4x more data. So these results are already quite good and quite compelling. But as it turns out, we could probably make it better, and this is something that we're still striving to do. Before, I talked about holistic embedding, but I want to revisit this a little bit. So when we talk about describing error data, when we look at the embeddings, we see here that in a particular caption for this is a pedestrian is crossing the street and the car appears to be slowing down. But again, our goal here is to correct erroneous behaviors by getting good behaviors in similar situations, right? But this caption does not tell us whether or not this is a good behavior or a bad behavior, and that's a problem. And so a very good example of this is, let's say our targeted error is again simplified here. What we want isn't a example like A and B, but they will have similar captions, right? There's a pedestrian crossing the street, et cetera, et cetera. What we want is C. There's a pedestrian crossing the street on the right-hand side, which is where we want to go, but we need to stop. So therefore, what we need to do here is actually being able to capture causation in the actual caption itself. And it turns out causation is a well-studied field as well. And so instead, to capture causation, we can use something called embodied reasoning. And we can turn our embedding space into embodied reasoning. So if we look at embodied reasoning, what does that mean? So we can break down reasoning into two main components: common sense reasoning and embodied reasoning. Common sense reasoning are things you see in your daily life, like physics, science, time, and space. Embodied reasoning is if you have an agent that interacts with its environment and therefore must reason with its actions and its consequence with the object. Like if I pick up this bottle, I will lift it. And if I remove my fingers, gravity will enact and the bottle will fall. That is embodied reasoning. And for us to get embodied reasoning automatic pipeline, what we do is we can take these videos And we can actually put it through a reasoning model, such as Cosmos reasoning, and obtain the reasoning information about why these particular failure points happened. The video failed, the driving failed because we did not adhere to yielding, right? Or we did not clear the intersection before actually moving. So understanding why these data points failed and then encapsulating it is important. And then we can simply put this through a text transformer and turn it into a reasoning embedding. And this is the most simplest way to get this done. And again, we're leveraging a model off the shelf, which means you don't have to train it at all. So this is an example of an embodied reasoning text. It's very long. This is an actual failure case where the car is driving and doesn't look both ways and it just hits a car. So we have a list of reasons for the crash activity, and we also have the description of what happens, right? And so now we have decided, okay, embodied reasoning is great, but actually, what about the proxy for the data space? And before we were using the train set, and I want to recap again that we define the data space as a space for all data where that related to a single task lies, right? And the larger that space, the better it is. And we have used holistic data embedding, and we actually started this holistic data based on the train set. But that was for detection task, which is very mature, right? But if we now go to driving, this is a fairly new task, and we don't have really well-defined terminologies for self-driving. And as it turns out, that means our training data set for driving is rather ad hoc, and our categorization is also very ad hoc. And if our goal is to push out a product and fix deployment, something that we really need to care more about is the test data space, because our goal here is now work in the real world. And so what we are saying here is that all possible testing data is the one that best represents the data space related to this specific task. And so we change our data space proxy from train to test for this particular task. Okay, so what does this look like? This is very ugly, but it gets the point across. So we have clusters on the test set, right? And we have a bunch of test data. We can remove that test data to make sure there's no test time leakage. And now what we do is we have errors. We can classify them into each classifier. And then we can find similar data points in the data pool to that particular failure within each cluster. And what we can now do is take a look at the training data points and also map them similarly onto these clusters. Then we look at any data point in the train that is very similar to the data pool, right? And what we're saying here is that this is a duplicate. If we add these two blue points, it's not going to add any value because we already have that in the train set. So instead, we just remove it. Again, this is the deduplication problem that I spoke about earlier. And through this way, we can incorporate those data points from the data pool that is similar to that failure back into the train. And because we're doing this in test time through the structure in the test space, we're making sure that we are increasing the diversity in our train space. Now, of course, there's also the possibility that errors can fall outside of these clusters, right? And this is an out of distribution problem. And when we talked about the clusters from the test, we assumed an ideal test case, but that is almost never true. It's always a proxy of the test. And so if a data point falls outside of these clusters, what this means is that we must adapt our test set accordingly. So you need to now add these failure points, or specifically any data points that are similar to that from the data pool, into your test set. And so you can continuously update your test set and therefore update your training also along the way. Okay, so I just talked about error-driven for curating a data set, and this is when we were able to collect data. And I want to briefly touch upon this because that was assuming that we can actually find these data points in the data pool. But what if we can't? And this is especially true for rarer cases. And this is where synthetic data comes in, generation. So I talked about the Cosmos reasoning. And in order to get synthetic data, what we can do is actually take these captions where we saw what the problem was and take the inverse of that. So what is the opposite of bad is good. And that's exactly what we want, right? And because we have these captions, we can now use those as prompts for a generation model and actually generate a set of data points that can address our failures. So for us, again, this is the example of a failure case, right? And at NVIDIA, we're able to essentially take these captions and generate synthetic data that mimics this failure case, but instead we do the appropriate thing and we stop. I'll let this linger a little bit. So I think this is quite cool, right? So in this way, we're able to get any data points that are rare that we don't have in our existing data pool. Of course, there are limitations to generation. I just showed you some nice ones, but I'll be a very terrible researcher if I just said this is solved. It's not, okay? If you look at these videos, you'll see the traffic lights look weird. That's because there's two red lights, and on the right-hand side, there's a red and a green, and this is just not factually true. So, generation have its limitations, but it is a good starting point for trying to generate like rare cases that it's difficult for us to collect in the real world. Okay, so the main takeaway message here is that reasoning is a powerful tool, and we can understand our bad behaviors and convert them to good behaviors. And if we have bad behaviors plus reasoning, we can collect or generate the right data. And lastly, your task is really important. And depending on your task, you need to decide which data set you need to use to create your structure. Now, this is the end of the talk. I want to talk about some available tools and code that we have. I went through a lot of stuff today, a lot of which can be found in this slide here. There are papers and codes available, as well as tools and tutorials that I was not able to cover today, but they are on this slide here today, and you can check out our website, which is going to be updated very, very frequently. And we will have YouTube videos as well that I think is like 4 or 5 hours long that covers this even more in depth and with code in it and hands-on tutorial. It cannot be released because of a CVPR mandated embargo, but in 2 months' time, we will release it when we're allowed to do so. So that's it. Thank you so much. Someone that I want to really thank is Maying and Jose, who's obviously here today. But Maying could not be here due to visa reasons, but she was very much my partner in crime in all of this.